Today, we are, for the zkStudyClub, we are hearing from Michele Orru, who's going to be talking to us about Gemini. So welcome, Michele.
Hi, hello, everyone. My name is Michele. I am a postdoctoral student at UC Berkeley, and in this work, we try to study how to prove instances that are very, very large. So we're concerned with proving circuits that have a very big size. And this is joint work with Jonathan Bootle, Alessandro Chiesa, and Yuncong Hu. So we're going to talk about zero knowledge proofs, in particular about succinct arguments. So we have this usual conversation between a prover and a verifier. And at the end of this protocol, the prover should be able to convince the verifier that there exists a witness for which the relation is satisfied. What does it mean in argument? It means that we will focus on these kind of dialogues where security will hold computationally, and succinct will mean that the verification will be sublinear in the size of the witness. Actually, I will be talking about arguments with preprocessing. What does it mean? It means that the verification time is even sublinear in the size of the statement. So the verifier is like super efficient, and we're going to focus on, again, on these sort of interactive protocols between prover and verifier, where security holds computationally. With this kind of arguments are pretty well studied, no? Like SNARKs belong to this space, and proving time is either linear or almost linear, like n or n log n. For most protocols that we deploy in practice, verification time is either constant, like a constant number of pairings. No, this is the case of Groth 16, or it's like logarithmic. This is the case of things like Spartan. And however, the proving space is still sort of linear, and this is not this linear factor is actually like very large. And in fact, if we were to try today to prove circuits with like billions of gates on like modern provers that have been implemented, for the most part, they would sort of start crashing at around billions of gates. And so there is really no way today to run a prover for a large circuits. And that means that for me, at least, one of the biggest sort of constraints today is not anymore proving time or verification time. We've been working on that for a long time. It's really the space, the problem. Yeah, also for the implementer, and try to give more details, like when we try to run these instances, we also give them, like we've been running them on like big machines, and even running on big machines, like the kernel just doesn't want to allocate so much memory for us. Even like relaxing and allowing for overcommitment to the out-of-memory manager. As an example on why we're interested in these sort of problems, take, for instance, like a compression function for SHA-256. This is around tens of thousands of gates. If you do it like 100 times, because maybe you're checking a bunch of Merkle trees, then you're already outside benchmarks that happen in papers. If you do it 1,000 times, then you are far outside modern implementations, what can be handled by modern implementations. And this is the case, for instance, of, I don't know, zk rollups, no? Where you have to verify a lot of transactions at the same time, then you clearly have a very large circuits. And it's not clear how to do it in practice. So there has been a sort of a quite long literature, a quite long line of research on how to make arguments that are space efficient. For the most part, they are TCC papers, so they don't come with an implementation. But I think the initial line of research was exploiting, for the most part, recursive proofs. What does it mean? It means that there is this idea that I can divide this big circuit into chunks, and then prove these chunks singularly, and then make a proof that says statements about the single proofs that I made on little chunks. And with this, I can actually build things called complexity preserving SNARKs, that are SNARKs that preserve both time and space up to logarithmic factors, actually polylogarithmic factors. And this polylogarithmic factor, it's not really clear where how big they are. So it was mostly theoretical work. And more recently, there has been this interest in developing provers that are streamable. What does it mean for a prover that is streamable in practice? And this is the way that I wanted to think about it, is that you have a prover that is reading a file sequentially, and it's outputting a proof. And it is trying to use as little memory as possible. No, and the input comes sequentially like this. That was a nice animation. And then, but in practice, you can also imagine that I'm really downloading this instance from the internet. No, I'm downloading from somewhere else. I'm running the prover. I want the prover to just go as long as it can, and then output the proof, but without without using too many resources from my system. And I want to be able to sort of fine tune the prover to that. In theory, the way that we model streaming provers is that we have this Turing machine that instead of getting as input the witness and the statement, the private and the public input, it's getting an oracle access to a stream. What does it mean, a stream? It means that this prover this Turing machine can ask to this oracle, give me the next element, give me the next element, give me the next element, or reset the stream. And after running, again, in logarithmic space, it is going to output a proof. It's all clear up to now. I see 2 messages in the chat. Okay. Yeah. So in this work, the main contribution, I think, is this idea of elasticity. We define an elastic proof system to be a proof system where you can run both in 2 configurations. One that is time efficient, and we'll see how fast it is, and one that is space efficient. At the end of the execution, the prover outputs the proof. This proof is the same. The verifier can verify this proof and couldn't care less about which configuration has been running the prover on. Okay, so very simple idea. And we show that this thing actually works. Like there exists arguments that satisfy this property. We prove that there exists an elastic argument with preprocessing that is succinct for circuit satisfiability that has 2 realizations. One that is runs in linear time, and one that runs in log space. Okay, and again, this proof will be independent from the prover configuration, and the verification time will run in logarithmic in size logarithmic with respect to the size of the statement.
Can I ask you a question there?
Sure.
So by independent, you mean it's an indistinguishable distribution of proofs with the 2 kinds of prover?
Yeah, I mean that the prover at the end, the output of the prover is exactly the same.
I see. Okay.
Like the algorithm admits 2 different implementations. The next message function of this interactive protocol admits 2 different implementations.
I see. Okay. So the whole protocol will be, the transcript will be identical for the same.
Yeah, and there is going to be something very cool about our protocol in particular, and it's that we will, as we will see, we will be able to move from the space to the time efficient implementation. I'm sort of dropping this idea for now and letting it rest in your mind. But the second thing is that specifically the space efficient prover, that this complexity for running the space efficient prover was already known in previous literature. However, we improve on it in that for specific types of circuits that are, for instance, finite state machines or hash chains, then you can actually get this down to n log n. This log square factor really comes from like weird metrics, weird R1CS instances. And I'll get also to what is R1CS in a second. But
I might also have a question.
Yeah.
So you sort of have a time efficient version and a space efficient version, and the sort of trade-offs between the 2 are quite extreme. Do you also have like everything in between in terms of that trade-off, or do you have to go for the extremes? So something that's like a little bit time efficient and a little bit space efficient, would that be something that you would cover?
We will see how to go to that. Yeah.
Okay.
But the fine tuning is not asymptotic, however.
Okay.
And also,
so you're sort of saying yes, but you don't necessarily know what the asymptotics are.
No, it's yes, but I'm playing with constants, and as we will see, constants will be very important with these log factors.
Okay, I understand that. Thank you.
And yeah, so I think if I have to place this work among like the sort of various literature, we have like different sort of abstract protocols. No, these are what we call IOPS. Sort of, I'm going a bit more in detail, but then I will sort of keep talking high level. So this is a little parenthesis for the more technical people. If I have to think about the abstract protocols, generally we think about queries that can be over vectors. No, I can make I have a vector commitment and I'm asking for inner products, or I have a multivariate polynomial commitment scheme, or I have a univariate polynomial commitment scheme. Generating protocols for vectors, it is much easier than generating them for univariate. However, it is much more difficult. No, sorry. Yeah. And however, it is like the set of the efficiency changes, no? Like univariate protocols are much more efficient. And in particular, we know how to build a system that have like constant number of pairings for when they are univariate, but we don't know how to do it, for instance, with multivariate protocols. And up until now, like before this paper, we knew how to do succinct arguments that would run in linear time in the multivariate setting, but it was not clear how to do it univariate. This is what we do, no? We say that we can do a univariate. In particular, we will build a univariate sum check that runs in linear time, and the verifier will be logarithmic. And that's funny because really you can see this trade-off, no? Where the log factor, if you accept the FFT, goes up to the prover. And if you don't want to do an FFT, you want to stay linear, then this log factor will be dealt by the verifier. And I think there is really like this trade-off that you're doing where either the n log n is taken care of by the prover or it's taken care of by the verifier. And in addition,
I'm slightly confused. Isn't the multivariate case a generalization of the univariate case? So
yeah,
you would expect that. Why do you need a new result to get P's of O n and V of O log n?
Because if I have a univariate protocol, then I can use a multivariate polynomial commitment scheme, but not vice versa. If I have a multivariate query, then I don't know how to translate it into a univariate query. And we will see later today how to build it. And the second thing is about the space efficient protocol that we knew also how to do it multivariate, but we will see how to do it also univariate. And yeah, this proof system will be for R1CS. Why did we choose R1CS? Because it's one of the, I would say, most common ways of translating a circuit into an algebraic relation. And in particular, the sort of, if I have a circuit C, then there exist matrices A, B, and C, for which there is a Z. Like if I know an input, then I can find this Z such that this relation is satisfied. Oops. What does it mean?
I guess you're going to go on to this later, but are you assuming sparse matrices or?
Say it again?
Are you assuming that these matrices are going to be sparse?
Yeah, I will be assuming that these matrices are going to be sparse. And yeah, so what do I mean by this? I mean, if I have an arithmetic circuit. What does it mean arithmetic circuit? I have addition and multiplication over field elements. I have n wires and m gates. Then it is possible to build matrices, again, A, B, and C. Those dimensions will depend on the number of wires and gates, such that and how do I generate these matrices? No, I will put in each element, each row of A, the left input of the nth multiplication gate. So over here, I will put 1 for Z0, 1 for Z1, because I will go through additions, and then zeros everywhere else. Over B, I will do the same. I will put, however, the right inputs to the multiplication gates. So I'll put zeros in Z0 and Z1, and 1 for Z2. And zeros elsewhere. Now, if I do this inner product, no, I get Z0 plus Z1 times Z3 is equal to times Z2 is equal to Z3. And in C, in fact, I will put the output gate. And I will do so for every multiplication gate. And there you go. If I have a circuit that is satisfied, then I will be able to construct this Z such that this relation is satisfied. So our contribution is now like another one of our contribution, and I think it's necessary, when you start talking about streaming, is how do you stream this R1CS relation? And we sort of try to define it, And when you stream R1CS relation, this is really what the prover will get as input, You will get the stream of Z. What is the stream of Z? Z is a vector, so I will give you them element by element. I will give you each element in Z one by one. The matrices A, B, and C, I also want to give you a stream of them, and I will give it to you in either row measure or column measure. And there are two ways in which I can iterate for them, right? Because it's like two-dimensional. And yeah, as and I will assume that they will come in a sparse notation. They will be sparse. The representation will be sparse. Finally, I will also assume the stream of the computation trace. What is the computation trace is the product AZ, BZ, and CZ. Now, this clearly I can do it even in linear time if I can, if the metric, I can make assumptions on the matrix itself. The metric is quite simple, but otherwise we just assume that this is already pre-computed and the prover just has it as input. Okay, so the theorem works like this. You have an idealized protocol that is elastic. You take a polynomial covariance scheme that is elastic. You compose the two. You have an SNARK that is elastic. So I'm going to focus now on the idealized protocol and some particular subprotocols that I think is relevant here. And then I will go towards the commitment scheme. In particular, I will focus on inner product because I think sort of the inner product is the cornerstone of all of these protocols for building R1CS satisfiability. Because we are always talking about, over here, we're talking only about linear relations. So as soon as I prove inner product, then I have everything else. Okay, so there is something that is already elastic and that we know how to do. And these are sort of the sum check family of protocols. And in a lot of these protocols, I am reducing a claim about an inner product from statements of size n to statements of size n divided by 2. And then I will sort of recurse over these instances until I get a statement of size 1 for which inner product is trivial and can be immediately checked by the verifier. So what do I have? I have this protocol that runs log times, that runs for log rounds, and each round it's public coin. So at each round, the verifier will send me a random challenge. And the verifier will be computing the next instance and send like some messages along the way. But the next instance can be computed, for instance, by taking a linear combination of the even and odd coefficients. Or another way is, for instance, the left and right part of the polynomial. Now, note that the left and the right part is not really streaming friendly because I cannot jump around the stream from the n0 coefficient to the n divided by 2. Even and odd is sort of the more streaming friendly way. But anyway, there are many ways in which I can fold recursively the stream. And if you look how I go to the next step, at the end, I will end up sort of this term that will be sort of dependent on the randomness of the verifier. And in fact, the last round can be seen as a multivariate polynomial evaluation. And yeah, so I want to show you how this can be done, but actually, I don't know. Do you have questions so far? Okay. Okay, let's go ahead and then I'll converge to these if I'll go into more detail about the sum check protocol if you want. But for now, what I want to say is that this, we know how to do it in linear time. It's easy to do it in linear time if I assume random access and that I can store linear memory, because I can take the polynomial, take the linear combination, and then take the linear combination again of the even and odd coefficients, and how many operations I'm doing. I'm doing n divided by 2 plus n divided by 4 plus n divided by 8, and so on and so forth. This is linear. And so the question is now,
is it n log n though? Because you have log n rounds, and is each round on?
No, because I'm folding once for each round. So oops, I'm going all the way. For the first round, I will be doing n divided by 2.
The usual
then I will
argument
be
for why
doing,
it's, okay.
Yeah.
Why it's linear.
Yeah, and so this is the reason why sum check can be done in linear time, and this is also why I said that we know how to do our proofs in linear time.
Yeah,
now
because the size of the instance is reducing each time. That's fine.
Yeah, yeah. Now the question is, how can you do the same in a space efficient way? What does it mean to do it in a space efficient way? Again, it means that I have my instance. I don't have it as once. I have it as a stream. No, I have so the elements one by one like this. And the way to do so is to keep a stack. And then I take the elements and I start eating them one by one. And as soon as I end up with 2 elements at the same level, I will fold them. And I will put only this element in the stack. Then I will keep eating elements as soon as I have two elements at the same level that belong to the same sort of polynomial, I will fold them together. No, I'm folding even and odd coefficients together, and I will replace it here. Then I will continue folding because there are two elements at the same level again. And the algorithm goes like this, and so on and so forth, until I reach the folding that I need, and this I can return in a string fashion. Now, how much memory am I using? I will have at most 2 log n elements in this stack, so I'm still logarithmic. How many operations am I doing? Well, in order to generate this folding, I will have to compute again n divided by 2 multiplications plus n divided by 4 plus n divided by 8, so on and so forth. So it will be n, the complexity, in this case, for a single round. No, so I will have a proving algorithm that for generating in terms of space, it will run like in linear time for each round. So overall n log n time. And there is a particularity, however, here, and I guess in this general structure of the subject protocol, is that I can fix a memory budget. No, I can fix a threshold and say, okay, I'm going to run the prover in a space efficient manner until I reach a certain threshold where the intents can fit in memory. And then I'm going to switch to the time efficient prover because the configuration is the same. No, the output messages of the prover are the same. And then I will continue running with the time efficient one. So I will have at the end some check protocol that we run as efficient as state of the art for like normal instances. And if the instances are larger, then I will have to resort to these sort of streaming techniques. And so we end up with a proof system that is, again, as fast as we know how to do it, but it also, you can just let it run if you have a larger instance. So once you build this idealized protocol, no, and you have at the end, I said, one of these multivariate evaluations to deal with. And but I told you that I have a univariate protocol. And in fact, what we do is the way that you sort of formalize this, no, is that you have an idealized protocol where you have this multivariate query. In reality, how this is done, you take a multivariate polynomial commitment scheme, the prover commits to it at the beginning, and then you ask for an evaluation of it. What we show in the paper is actually how to reduce this query into a univariate query. And in reality, you will just have to use a univariate commitment scheme. Oops. Why is this useful? Why do we care about this? Because we know how to build very efficient univariate polynomial commitment schemes. And verification, for instance, in univariate commitment scheme is like 2 pairings, whereas in the multivariate scene is like log n pairings. So we're really changing a lot in the constant terms over here. And I want to show you how this is done. And so maybe I want to open a small parenthesis on here on this. So I will stop sharing, and then I will start sharing from here. Okay, so when you have a multivariate, when you have a vector, no, you have these coefficients that I can write as bits. So like this. Does it make sense? And when you ask for a multivariate evaluation, f evaluated in R1, R2, R3, and so on, until Rn, you're essentially considering the sum over I of all the bits. You're summing over f, and then I have all the little bits here. So I have B1, B2, B3, up until Bn. And then I have R1 that is taken or not, depending on the bit. R2 that is taken or not, depending on the bit, and so on and so forth. Okay, this is what I mean by multivariate evaluation. This thing can also be written as the inner product between a vector f and this tensor product. What is this guy? This product, 1rj, is equal to 1, R1, R2, R1, R2, etc., etc. And you see, I have that 1 goes with the constant term, R1 goes with this term, R2 goes with this term, R1, R2 goes with this other term. And that's exactly what I have written here. Okay, so if I go back, if I were to go back to the slides, like what I'm actually asking with the multivariate polynomial evaluation, it's really how to deal with this case. So let me stop over here and share the screen again. Okay, so this is the way that I'm mapping it as a sort of as a relation between vectors. And again, this is the way what I mean by this tensor product. And the question is, how do I implement it with univariate polynomial queries? And the idea is pretty simple, actually. I can take a polynomial and I can split it into even and odd coefficients. Now, if I think of the even and odd coefficients, the odd coefficients are the one that will be multiplied by R1. No, there will be one for which that bit is set. And in addition to that, even and odd, no, they have a half the degree. And this is what allows me also to do folding. And in particular, they can be obtained, and this is sort of well known, no, already, like we use these tricks a lot in the community, that you can obtain an evaluation of even and odd polynomial by using an evaluation of f in plus and minus x, a univariate evaluation of f. Okay, and so in order to compute the folding, I can compute it by asking evaluations of f in plus and minus x. I can ask evaluations of f prime by relying on evaluation of f in plus and minus x. What does it mean? It means that I can check on a multivariate evaluation in the following way. I send you commitments to all of the foldings of the polynomial, so that even and odd folding that I showed before. Then the verifier will send me a challenge. And I can, the prover will have to check that then the first folding is generated correctly from the first one. How? By asking evaluation in plus and minus beta, a random point. And then I will do so on and so forth until I reach the last, the last folding. And the last folding is really is a constant polynomial. So that will be the multivariate evaluation that I am looking for. Now, this protocol is, why does this buy us anything? Because in KZG, I know very well how to batch multiple polynomials, evaluations over multiple polynomials and over multiple points. Here, I'm doing 3 points and I have log n polynomials, but the proof will still be a single group element, and verifying the proof will still be very efficient. And this is sort of the big advantage that we have over multivariate techniques. And also to say something more interesting, no? If I have a multivariate IOP, if I have a multivariate protocol, I said before, it's easy to build a univariate one. Now we show that you can also do the vice versa. And this is also, again, more efficient than what we knew so far in the literature. If you think about other polynomial commitment schemes that are multivariate and that allow for a trusted setup, you still have log n pairings. And in this case, you have only a constant number of pairings. And it's interesting to, well, going very technical, in PST, the proof is works by reducing the remainder over and over, whereas in this case, we're reducing the quotient over and over. I'm hand waving an idea here, but like there are relations between the univariate and the multivariate. Well, then at least for me, it has been fun to explore them in this project. And all these foldings, they can be done using a single pass over the initial stream. Why? If I think about space efficiency, whenever I'm building the nth folding, I have to go through the ith folding, like all the previous foldings. I have to generate them in memory. So I might as well like use them and start committing to them or start working on the opening proof. So I need only a single pass over the stream in order to make all of these. Okay, now from this you can climb up and yeah.
I have one quick question. You had mentioned PST. What does that stand for?
I forgot. It's
No, you just mentioned it just now, right?
Yeah, it's the name that we use for polynomial commitment scheme. I forgot. I don't know. I honestly don't know where the acronym comes from. It's a signatures of correct computation. I think the paper that that displays it.
Okay, thanks.
I don't know what is the acronym for. But yeah, the correct reference is signatures of correct computation.
Cool.
And I mean, you can, once you have inner product, as I mentioned before, it's pretty easy to climb your way up to R1CS. And whenever you have to deal with holography, you have additional protocols. Sort of a technical note here is that when you try to do streaming over instances for like some subprotocols, it is really non-trivial. For instance, when you try to build preprocessing, there are these lookup protocols that are extremely useful. And there are, I would say, two big protocols for doing lookups that we use today. One is plookup and one is memory checking. Plookup, we know how to do it in a streaming fashion. Memory checking, we don't know how to do it in a streaming fashion. And yeah, it's not evident how to do this protocol in this way. And I can go into, oh, thanks, I see now the question. I can go into more detail if you want about this. But for now, I just want you to I just want to take like a sort of a bird's eye view. And we built this sort of idealized protocol, and now we want to compile it down with a polynomial commitment scheme. And we want to build it in such a way that it is elastic. And we end up using KZG. And KZG, it can be built in a streaming fashion. Again, as a reminder, in KZG, you have this commitment key, which has like these consecutive powers. And in order to commit to an element, you're just taking the linear combination of the coefficients of f with all these powers. How do you do it in a string fashion? Well, again, f, you have the coefficients 1 by 1. And the commitment key also, you have the coefficients that come, like the elements that are coming 1 by 1. And it's easy to build a commitment in this case, no? You take the elements, you multiply them, you take the elements, you multiply them, and so on and so forth. The real problem is how to build an opening proof. In KZG, an opening proof is the quotient, the Euclidean quotient of f with the polynomial x minus alpha. No? If you consider this equation, the reminder here is f evaluated in alpha, and the quotient is the commitment to the quotient is what constitutes the proof. And then this proof will be checked in the group. But how do we build this quotient? And this we know how to do. It's essentially what we call Ruffini law, to be fancy, but it's like pen and pencil sort of a division. Because if the polynomial has low degree, polynomial division can be done efficiently in a streaming fashion. How do you do it? You take the stream of f again, the coefficients 1 by 1, and then you keep the stream of the quotient by holding the last element. And the leading coefficient is also the first element of the quotient. And then by computing this formula, which is again is Ruffini's law, for computing the next element. And then you throw the previous coefficient as a stream. And then so you need to keep only one element in memory. So again, you're keeping a very low memory footprint in all of this. You can also do batching. And this is sort of related to a more recent paper of Bonnet, Justin Drake, and others, where instead of considering the evaluation by the division of like the degree 1 polynomial, no, you consider the division by the polynomial that is 0 in all of these points. And the idea is the same. You just have to keep track of more coefficient. And in our case, remember that we need to evaluate only on 3 points. So again, these batching techniques can also be used in our case and can also be done in a string fashion. Once we built all of these, we have been trying to implement this down like in Rust, and we built it into artworks. And this was quite an engineering effort because we had to build like all of these things into polynomial commitment schemes. No, we had to build KZG. We have some students working on PST right now, and on the top we had to build like this tensor check. No, and all these protocols are built in a modular fashion so that it can be reused by other people. For instance, also in KZG, we have these batching techniques that were not previously developed. And then on the top of it, you need to build this sort of inner product, univariate inner product that we have. And from here, you can build a SNARK, or you can go up and build a preprocessing SNARK. And that's what we do. So you end up having to build also lookup protocols and ground product protocols. We also have memory checking on the way. And all of these, no, you don't have to implement it only once, you have to implement it twice, one time efficient and one space efficient. And then you have to find a way of switching from one or to the other in the middle of the protocol. And so I guess like sort of the big outputs of this is that now, like some parts of it, we have been pushing them into artworks, and one of the side effects of this is that, for instance, right now into the polynomial commitment library in artworks, you have 3 different implementations of KZG. And one project for novices that would be fun, I think, is to try to merge them and to find like what can be moved into a single library that can have also streaming functionalities and batching on the top of what is, for instance, already used in Marlin. And the second thing that I wanted to share about the implementation is that down to earth, like to be like very concrete, at the end of the day, all of these streams are just iterators. So you're literally embedding, like when you end up working with them in Rust and you want to keep it use dynamic types, then you end up having to embed the entire computation that you make in the tree in the type. So it is a bit of a pain to get this done correctly, but you essentially have 0 overhead for like composing streams. And so, for instance, you end up having streams that belong to a matrix that you multiply by other vectors over which are doing, for instance, algebraic hash. And so you end up composing these streams and you end up with these huge types, but that is the price for having a very efficient protocol. There are other implementations of space-efficient provers. However, they rely more on the streaming functionalities of asynchronous Rust, and that is a bigger overhead. And so we've been running some benchmarks, and this sort of perhaps is sort of also related to the question that Mary gave at the beginning. Oh, there is a question. Oh, right. Okay, thanks, Larry. So in practice, while I would say that a lot of works in the past were stopping at like, I don't know, millions of gates, in our case, we can go up until 2 to the 37. So we're talking about hundreds of billions of gates. And even if we try with our own implementation to just run like a time-efficient prover on a very large machine, we cannot go further than 2 to the 27. So all of what you see over here is space that can be harvested only by using streaming techniques. We also do it the same, and if we run it for preprocessing, we stopped a bit before at 2 to the 34, but the morale is sort of the same. But I wanted to sort of focus on one thing, and that's that despite the time is a quadrat, like there is this log square factor, at the end of the day, the graph is linear, and it's linear for a reason, because the bottleneck in all of these protocols are really the commitment schemes. The group operations are really, the public key operations are really what's taking most of the time. And the log factor, I don't even see it for these huge sizes. And the same can be said for memory. Despite the memory grows logarithmically, once I set a good budget, in our case was like 1 gigabyte, you can just let the prover run for whatever instance you care about. And despite there is the log n factor, the memory will stay pretty much constant. And so, this is it. So wrapping up, we contribute with this idea of elasticity, where you have a time-efficient prover and a space-efficient prover, and you can sort of merge them together and have something that can be done for very large instances, but can also run very fast. Yeah.
Can I have a look at those performance graphs again?
Yeah. Oops. That is with parallelism.
Yeah. So how much parallelism is there a way of doing an apples to apples comparison with other implementations?
I don't remember. I would say that in terms of speed, this is pretty much the same as Spartan. And in terms of parallelism, I would say it's, I don't know. Wait, I would say we're around 30 CPUs.
Okay, so not a consumer accessible CPU. Okay.
Yes, if I have to, I run benchmarks on my MacBook Pro 2019 over this, and I'm like twice as low. So if I go, I would say that if I were to go for an M1, M2, I would get similar performances to these.
Okay, thanks. has a question for me.
Yeah, I think there are some things that are really hard with streaming, and one of them is, for instance, even just the order of folding is not immediate. Again, folding by now, I guess we know that even and odd and left and right is pretty much the same. But if your implementation is already using left or right, then there is no way I can do the tip streaming. Another scenario is when you do KZG. Let me go back over here. When you do KZG and you're building the quotient, you need to start by the leading coefficient, because otherwise there is no way I can compute the division in a nice way, in a streaming fashion. What does it mean? It means that all the vectors need to be streamed by the most significant degree to the least significant degree. And this, paradoxically, for instance, affects also the entry product protocol, where in the entry product protocol, in what is also called the ground product protocol, I have to send you this vector of accumulated products. No, I start from the first one, and then I multiply the 2, and then 3, and then so forth, and so on and so forth. And then I prove something about the last one. In these cases, if I start from the most significant one, then I have also to adapt the entry product protocol so that the accumulated protocol doesn't start, the accumulated product does not start from the least significant coefficient, but must also start from the most significant one. So there is also some, there are really some things that you need to think about streaming that really affects different protocols at the same time. And
but if you wanted, for example, to implement a scheme that was compatible with yours, but that didn't need the large instances, then you could have a simpler scheme that was compatible. That was basically just the algorithm that you're using below the memory threshold.
Yeah, for sure. And I think, and I think really the contribution is for whatever is after that. In any case,
of course, yeah. It's just
besides
for things like standardization, it might be useful to.
Yeah. And I think the only additional thing is the only additional thing is this translation, this tensor check, how to translate multivariate queries into univariate one. That is, I guess. Somewhat general, and that you could do with or without streaming in a nice way.
Yeah, I guess. It seems like this, like the idea of streaming. I guess I think I like streaming across the internet. Like if you have a client that wants to basically use a powerful server to compute the proof for them, I kind of like what kind of bandwidth and other requirements are required for the client in this case.
Oh, nice question. I think I don't know what kind of bandwidth requirement would be needed. What I know is that you will need to make log passes over the initial streams. So if you are taking instances that are this large, you're probably transmitting gigabytes in terms of memory, in terms of data. Does this answer the question? Like, yeah, I have to make log passes over the initial stream in order to perform a proof.
I guess you can stream it to some storage device that is close to you, and then stream it again log n times.
Yeah, and I think this log factor, like I think it's really it would be very hard to imagine a protocol that does not need to stream over the instance multiple times. No, there is something about this proof that is also like binding to the fact that that cannot be extended. No, I have to make multiple passes over it to make sure that this thing is not being extended further. The proof cannot be changed on that side. I don't know if this makes sense.
Yeah, that makes a lot of sense.
Yeah. Cool.
I mean, I guess the verifier has to check that it's actually getting the stream, the same stream multiple times, but it can do that using commitments or max. Or something like
the verifier is actually not needing the verifier, we didn't even care about doing streaming because the verifier is already succinct.
Oh,
That's one of the
yes.
pros.
Yes.
So it's only the prover that needs to do that, and the prover needs to deal with its own. Yeah. So yeah, the verifier has log memory and has log runtime because it's with preprocessing, right? So we don't even care about it. Yeah.
I guess you also mentioned, I see this was about R1CS, but did you consider other optimizations?
Other optimization, I think I'm guessing you're thinking of Plonk. And in Plonk, it's funny because if I have to think about that, then I have these matrices that are generally like thin but very long. So I think all the protocols that would be in Plonk are somewhat already dealt in here in this pile of things. So I thought about it. I didn't work out the detail. I would suspect that it would work okay. And also that streaming might be even less of a pain in the sense that with R1CS, you need to take care of these. You get additions for free, but you get them for free because you're doing these matrix vector products inside the protocol. And so I'm guessing that some of these things will, like you have smaller matrices when you're doing Plonk, and it seems easier to do like matrix vector products, and it seems also easier because you have so much redundant information in Plonk for working with. So I don't know the details. I haven't worked out the details. I had this little bug in my mind, and this is the only thing that I can share. It seems doable in any case. I would be surprised that this cannot be done. Does that answer the question?
Oh yeah, definitely.
So what's the largest sort of kind of realistic circuit that you've tried this on?
Not realistic. I've been trying to have students write hash chains because hash chains, you can very easily stream them.
Yeah.
But we're not still there. For now, we're just making dummy instances and just like running them.
I see.
Yeah. But it would be, I think hash chains are sort of the shortest useful thing that you might want to test to battle test. Yeah.
So what's the practical size of a proof?
I would have to check right now, but we're talking about log group elements and with preprocessing. I mean, you mean?
Yeah. Yes.
Let me open the paper. We're talking about 2 to the 35 instances that take 27 kilobytes.
Okay. Yeah. Mm-hmm.
And then it's it goes a bit linearly. So
Yeah,
well, with the log,
it
grows with the log. Say it again.
So that's kind of comparable to bulletproofs or something like that.
Yeah. There is this log factor that is always there. I guess that yeah.
Maybe
Yeah,
a
it's
few
very similar
times
to
larger
proof.
than bulletproofs, actually.
Say it again.
Maybe a few times larger than bulletproofs.
Yeah, but if you're doing pre-processing, then you need all that additional load from other subjects.
Yeah.
Yeah. Okay.
I don't know if you saw the question in the chat.
No. I think I replied to that.
Oh, you did already. Okay.
Yeah. Is there any chance your results could be extended to be backwards compatible with other schemes? Or why is it hard? And yeah, that was the answer that I gave before about, I think it's really hard, and there are like protocols where like really it depends on, like you have to think about what ordering does one need with respect to the other. For instance, this was the case of the polynomial commitment scheme. When I do streaming, I need to keep in mind that I will be going big endian. And when I'm using other protocols, for instance, the entry product protocol, then I need also to build the proof, keeping in mind that it's going to be big endian, the streaming part. So yeah, I don't know. It's a difficult question. I don't know how to do it.
Are there any other questions? I think if not, then I think we can wrap up. Thank you so much for the talk and sharing with us Gemini.
Thank you.
Thank you.
Thank you.
Yeah.
Thank you.
Cool.
Cool. Thank you.